I'd like to say a very big welcome to our 17th edition of News from the Lab. This is an event which gives members of the alumni platform, the alumni network, privileged access and insights into the diverse and exciting work happening at CERN. So thanks to all of you for joining us this evening. I know spring has sprung. It's great to have you with us. And today we're thrilled to shine a spotlight on the HL-LHC project and are delighted to welcome back a CERN alumna who's very familiar with this amazing project. She'll be moderating the event. So I'm really happy to introduce Irene Garcia Obrero. And she's a journalist and a communication specialist with a strong background in audiovisual and transmedia storytelling. So from 2020 to 2024, she worked as a communications officer at CERN's High Luminosity Large Hadron Collider HL-LHC project, managing content creation, audiovisual coverage, and event organization to enhance its visibility. Before joining CERN, she worked as a correspondent for Agencia EFE at the United Nations in Geneva, covering international affairs. Currently, Irene works as an internal communications and engagement specialist at TUI, where she focuses on strengthening corporate culture, employee engagement, and internal storytelling strategies. She holds a dual bachelor's degree in journalism and film, television and media studies from UC 3M, a master's in transmedia journalism, and is currently pursuing a master's in digital marketing. Irene, the floor is yours.
Thank you, Rachel, and thank you for this kind introduction. Good evening, everyone, and a very warm welcome to today's talk. It's always a pleasure to reconnect with the CERN community and stay updated on the incredible work happening at the lab. Today's talk is titled Introduction and Status Report on the HL-LHC Project, and I'm honored to introduce our speaker, Dr. Oliver Bruning, with whom I've had the pleasure of working for the last few years. Oliver is a senior scientist at CERN, specializing in accelerator physics. He has been involved in several flagship accelerator projects since 1991, including the commissioning of the Hera electron-proton collider at DESY, the LEP2 upgrade, and the LHC design and commissioning at CERN. Since 2021, he has been leading the High Luminosity LHC Project, which aims to significantly increase the LHC's luminosity and open new doors for scientific discovery. Today, he'll walk us through the latest updates, challenges, and milestones in the HL-LHC project. Thank you for being here with us, Oliver. We are very much looking forward to your presentation, but please, before I hand over to you, let me remind our audience that we'll have a question and answer session after the presentation. So in case you might be interested in knowing further about the HL-LHC project, please feel free to type your questions in the chat. And now, Oliver, over to you.
So thank you very much, Irene. So first of all, I would like to thank both of you, Rachel, for initiating that, inviting me. It's really a fantastic occasion to talk about the High Luminosity LHC project with CERN alumni. I think it's a very special occasion. So I thank you very much for that. And then, of course, I'm really delighted to see you again, Irene. Really, just to tell you, you're still very much missed in the project office. So very good to have at least this chance to interact with you. Very fantastic. All right, then I think I start with the presentation, if that's okay. So let me introduce to you the High Luminosity LHC project. And I have to see how I get this. I think I have to do, need the keyboard. So short outline of what I want to do. So I give you, talking about the High Luminosity LHC, I think I have to first start with the LHC to remind you of what the LHC is doing and has been doing so far already, and then to highlight to you what the High Luminosity LHC intends to do beyond the LHC. For that, I introduce to you for High Luminosity LHC the key project goals and the key challenges, and then we'll highlight and take you through some of the project milestones. And in the end, I really want to focus or showcase to you the IT string. So that's a test setup that we are building at CERN, which will really be the showcase for this year, for the second half of this year to come. And I invite you all to stay tuned and to follow the High Lumi news platforms in order to see the progress for this very exciting first test implementations of the High Luminosity LHC project. So moving on, LHC. So first, for those of you who are not that familiar with LHC, I remind you, it's a 27-kilometer circumference collider in the Geneva Basin between the lake and the Jura Mountains. It's the biggest accelerator and collider in the high energy physics field that we have at the moment. It has it features proton-proton, lead-lead, and lead-proton collisions, plus other ion species. I think one should highlight that in the last operation runs, we also had xenon, oxygen. So, but the main workhorse for the ion operations is the lead ion operation that we have in the machine. Then we have 4 experiments in total in the LHC, Atlas and CMS, which we call the general purpose detectors, which were designed before we discovered the Higgs particles. So we were looking for something for the unknown in the LHC machine. We didn't know quite yet where the Higgs was and whether we would be able to find the Higgs particle in the LHC, but we knew that at the collision energies of the LHC, there should be new physics. And these detectors were really designed to find anything that diverges from the, or diverges from the standard model or the Higgs particle itself. In addition, we have the LHCb and the ALICE detectors. So these are more special purpose detectors. LHCb is a beam meson detector that looks at the rare decays of beam mesons. This is a precision experiment. You can picture it a little bit like a keyhole experiment that gives you potential access to beyond standard model physics if there are any deviations observed in the measurements from the standard model predictions. And that's the main goal of this experiment. And then ALICE is a specialist for the ion collisions in the machine. Of the 27 kilometers, the LHC has about 22 kilometers equipped with superconducting magnets in the arcs, where the charged particles, the protons or the ions, are bent on a circular trajectory in total. And this is the track record of the LHC for the first 10 years of operation. So I picked here the results from the CMS detector. And you see that progressively over the first 10 years of operation, different color codes. And you see here that the performance increased steadily. And just to introduce to you the units on the horizontal axis, we see an operating year starting typically around Easter and then going to November, December, where we take data. And on the vertical axis, you see what we call the integrated luminosity. We express this in femtobarn. And again, for those of you not familiar with the unit of a femtobarn, it's just a measure for the amount of data that we collected in any running period of the machine. And what is really worthwhile to highlight here is that the data accumulation really increased steadily with every year of operations. And in the last year of operation, 24, we accumulated more than 122 inverse femtobarn. And again, just to give you an idea of the magnitude of this number, before the LHC started operation, the worldwide volume in hadronic collisions that was produced before the LHC took on operation was around 11 inverse femtobarn. So within 1 year, the LHC produced more than 10 times as much data volume for hadronic collisions than existed before the LHC started in its last year operation. That's a very impressive number. And another number to compare that to is the LHC was designed for total data production of about 300 inverse femtobarn. So we produced almost half of the initial nominal LHC design goal in 1 year. It's really a spectacular performance level of the machine in the last year of operation. So we produced more than 389 inverse femtobarn at 13 TV so far during the first 10 years of operation. We had the Higgs discovery in 2012, of course, really standing out. And we have now more than 100 inverse femtobarns per year in the production at hand. And we plan to run for another 1.5 years. So 25 is the last full year of operation. And then we will operate until mid-26 when the machine is scheduled to be shut down. And by that time, we estimate to have produced about 500 inverse femtobarn in the machine. So almost a factor 2 more than the nominal design goal of the LHC machine. So with that fantastic performance of the LHC, you might ask yourself, why do we need a high luminosity LHC project? So why do we want to have even more luminosity? I think one should highlight is that, yes, we discovered the Higgs in 2012, but many, many questions remain open and the search continues. We really want to know what are the Higgs properties, and Higgs properties means how does the Higgs couple to all the other particles in the standard model? The question is there more than one Higgs or is there only one Higgs? For that, we need to have more data, better resolution of the Higgs data sets. Then, of course, the search for any physics beyond the standard model, what we call the BSM physics. And we know from cosmology that there is dark matter and dark energy, where in the standard model, there is no description for that yet. So we need to find out what is the mechanisms or the answer to these big questions of dark matter and dark energy. And with some chance, hopefully the high luminosity LHC can shed some light on that with more data. So for all of that, we want to have more data. And just to highlight to you how the experiments work, is it's for them a statistical process. It's like rolling a dice and then looking at how well your dice is calibrated and formed. So doubling the statistical error for the experiments implies that you have 4 times the data volume, because the accuracy only increases with the square root of the data volume they have. So if you want to have twice the statistical accuracy, we need 4 times the data volume. And even at the very good performance level that we had last year in the LHC, that would imply 20 years of operation with the current peak performance. And if you then fold in that every 4 years you need to have a 1-year long shutdown to do maintenance in the machine, we would project operation of the machine up to the mid-2050s, which is really a very, very long operation period and impossible with the existing LHC hardware. So just to show you one example where the hardware reaches its limit for the LHC, I want to show you here the schematic layout of what the machine side looks like next to the detectors. So picture the detectors here on the left, Atlas or CMS. And then we have here the focusing quadrupole elements. So these are like optical lenses, but lenses that focus charged particles as they go through there. We call them our triplet layout. And then you see here what we call D1 is one of the separation recombination dipole magnets, which bring the beams from the 2 separated trajectories or apertures in the arc to one common aperture in the experiment so that they can actually collide with each other. On top of this, I overlay now the expected radiation that you expect in these elements after the nominal operation period of the LHC. So after we accumulated 300 inverse femtobarn. So again, this is the measure for the data produced in the detector. That was a nominal design goal. And you see here in red from simulations overlaid the radiation that you expect in these elements. And you see here that the entrance phase of the Q2A magnet that we call here Q2A, you expect about 27 megagray. At the exit of Q3, at the corrector package, you expect about 20 megagray. And in insulation vacuum material, about 35 megagray. And again, for those not familiar with the units, it's a measure for radiation deposited in a material, and 10 megagray is about the amount of radiations at which any epoxy material and Kapton or any other insulation materials becomes brittle and turns to dust. That means at radiation levels above 10 megagray, you really have to worry about the electrical and mechanical integrity of your magnets, as we use Kapton foils and epoxy materials abundantly in the coil productions. So at these radiation levels, really the mechanical and electrical integrity of the magnets is jeopardized, and you worry about generating shorts and interrupting the machine operations due to faults in the magnet. So you have to exchange the magnets at these radiation levels. So we project that the end of the LHC triplet lifetime is around 500 inverse femtobarn when we end the machine in 2026. And even to reach this 500 inverse femtobarn, which is almost a factor 2 more than the nominal design goals, we have to play some tricks. And the tricks we're playing is we change the polarity of these focusing magnets, and we change the crossing angles in order to spread all of this radiation as uniformly as possible over all the elements, so that we keep that under control and below the 30 megagray of radiation that we think we can digest. So we need to replace the triplet magnets at least if we want to continue the LHC operations after 2026 to keep the machine operational. And then, of course, the idea is you're not just replacing it with the technology that you have, but you replace them with something better so that the performance can be boosted and improved, so you can hope for even more data in the same time period than you had in the first operation period. So the high luminosity LHC goals in a nutshell is to prepare the machine for 10 times the data volume that the LHC has produced. So that means 3,000 to 4,000 inverse femtobarn, and to prepare it for another decade or 12 years of operation time. So up to the early 40s, we want to have the machine operational. And that requires the creations of radiation hard magnets that can tolerate up to 4,000 inverse femtobarn. So 10 times the radiation that we produce in the current LHC magnets. So how do you make a magnet more radiation hard? As epoxy and insulation materials are the ones which fail at around 10 megagray, the only way that you have is you provide active shielding inside your quadrupole magnets. And here's the cross sections through the magnets. The beam would go through the center. Here's what we call the cold bore that separates the vacuum from the actual magnetic elements. And what we plan to do there is we plan to insert active tungsten bars along the whole magnet in order to absorb the bulk of the radiation before it actually can reach the coils. So the coils, the epoxy and the insulation materials don't actually see most of the radiation. Here's a picture of what this beam screen then looks like as a prototype. So you see this octagonal shape of the screen. Then you see the cooling capillaries, and here you see the tungsten bars that are mounted on top of the beam screen in order to shield the magnets. And tungsten is a very heavy material, and just to give you one illustration of the challenge, so these magnets are about 8 meters long, and just the beam screen with the tungsten blocks weighs about 500 kilos, so half a ton that we have to insert with high accuracy into the magnets. Okay, so this requires larger aperture, and since the quadrupole magnet is defined by its gradient, that means the larger the aperture at a constant gradient, the bigger the peak field is. And for the LHC, we had 70 millimeters diameter with a gradient of 210 Tesla per meter. That translates to 8 Tesla peak field at the coils. That's at the limit of what we can do with niobium tie technology, the superconductor that we use in the existing LHC. We want to more than double the aperture. We want to go to 150 millimeters diameter for high luminosity LHC. In order not to increase the peak field at the coils too much, we back down in gradient. We only take 140 Tesla per meter, but even that implies 12 Tesla peak field, which is beyond the niobium tie technologies, and we need to develop a new superconductor, which is a niobium-3 tin that we chose for the high luminosity LHC. So we needed to develop a new superconductor, and we needed to implement longer magnets, which makes the whole magnet assembly and production more cumbersome and more complicated. And the special feature about niobium-3 tin is that differently from niobium tie, which is elastic, it's like a fiber. You can bend it, you can tear it, and you can shear it, and the superconductor is rather robust against that. Niobium-3 tin is like a ceramic. It's not a ceramic, but has similar properties in the sense that if you put too much force on it and you have too much impact on it, it will just crack. And once it's cracked, it will no longer be a conductor. So you have to be very careful in the way you handle this material and in the way you make your coils and treat them later on. So it requires larger aperture, new magnet technology, a new way of assembling all of these coils and the magnets in a cold mass, and all of this. Here's the cross sections of these new magnets, the way they look like, with a new design for how to assemble them. And all of that has been done in close collaboration with our US colleagues in America. So then I give you a summary of what we tried to change or plan to change in the LHC. So on top, you see the existing interaction region layout. So the detectors are on the left side. You see the focusing quadrupole magnets, the D1 and D2 separation recombination dipoles. And we replace this setup with this new setups where the triplet magnets are much, much longer. In order to recuperate some of the space, we now go from a normal conducting dipole magnet D1 to superconducting D1 dipole magnet. We move also the second separation recombination dipole magnet D2 closer to the interaction point to have some space between D2 and Q4. And there we will install the crab cavities, which I will introduce to you a little bit later down in the presentation. So in the end, we're not only changing the triplet magnets, we really change a whole set of new magnets. And just to show you a picture that I took from Ezio Tedesco, it's a whole zoo of magnets that we changed. It's the triplet magnets, there's the D1 and D2 separation recombination dipole magnets, then the corrector magnets for the orbits, and the nonlinear corrector magnets. So really a large set of magnets that need to be designed, prototyped, and developed for the High Luminosity LHC project. To comment very briefly on the challenges of making new technology developments, I want to look back at superconducting magnet developments in general. So here's a picture that I got from Lucio Rossi for the development of the niobium titanium magnets that started around in the late 70s with the first magnets produced for the Tevatron. After that, we got the Hera machine in the late 80s, which developed this further. Then RIG was a third machine with superconducting magnets in the arc bending magnets, and then the LHC really culminated this design and the technology in the early 2000s. The Tevatron really was a how do you call it, the pathfinder here, developed the technology, found many issues with it that had to be debugged. I think Hera was the first machine that really paid attention to the side effects of superconductors, like eddy currents and persistent currents, time-varying fields, optimized that design. RIG was in the first design which optimized the magnets for series productions and lowest cost in industry. And then the LHC really tried to put it all together to push technology to its maximum. What I want to highlight here is that all of this took about 30 years from the first conceptual design of magnets in the superconducting magnets in the collider to really pushing the technology to its end. So it's a long development process. For high luminosity LHC, we aimed at the installations at the years 2028 to 2029. So to be ready for that, we had to start the program, the development program already in the early 2000s, if you assume that you have a similar time span for the initial conceptual design to the actual implementation of the magnets. So we started with the first designs in 2000, and over the last 25 years, we really produced this steadily from first design concepts to prototypes, and now we're finally in the series productions, and we're well on track to install the magnets actually in 27, 28 as planned. So again, these are very, very long timescales for the technology developments. That brings me then directly to the overall timescale of the high luminosity LHC. So this is an overview. We started with the conceptual design, EU funded in 2011. 2016, we finally got the official approval by the CERN management or council. Official approval means we got a budget assigned, and we got the overall project milestones and performance parameters approved and fixed. We're now here at the beginning of 2025, which is the last full year of the Run 3 operation. 26, we will shut down the machine and take out the old aging LHC equipment, and we'll install the new high luminosity LHC equipment, and we plan to start the high luminosity LHC operations in mid-2030. So that's our overall timescale for the project. Again, the goals that are highlighted to you. So we want to increase the total data set by factor 10, which implies an integrated luminosity per year by about 250 ms femtobarn, over factor 2 more than what we produce right now in the LHC. And we reach all of that only with a very high operation and machine efficiency. And we have to overcome many, many challenges technically in the machine and in the experiments. And in this presentation, I will not be able to comment at all on the challenges in the detectors, but the detectors have an equal wealth of challenges that they have to overcome. And they also undergo immense upgrades during the Long Shutdown 3 shutdown in order to be prepared for the larger data sets for the high luminosity LHC period. Okay, so we need to overcome many limitations for the machine alone. So just to give you a ballpark figure, we talk about a 1 billion Swiss francs cost to completion project, ballpark figure. And now I turn to the main challenges and the main achievements that we have done for the project so far. So the first thing we had to think about is how do we provide the space for all the new equipment that we plan to install for the high luminosity LHC. Most critical are the new cryoplants for the additional cooling required for these high operation performance levels. And we decided in the end, we make a new tunnel structure slightly elevated above the existing LHC tunnel. So you see in light gray, the existing LHC tunnel, and in gray blue, you see what we have constructed for the high luminosity LHC. So it's a new gallery, slightly above and outside of the LHC tunnel, which is then connected with 4 link tunnels, 2 on this side and 2 on the other side of the detector, 1 big cavern, which has most of the infrastructure for the cryogenics installed it, and which makes the connections to the surface buildings that provide all the technical infrastructure services. And then in the main ring parallel to the LHC ring, we have then all the power converters, the quench protection equipment, all the new components required for the new high luminosity LHC elements in the tunnel. The new underground and galleries and surfaces buildings, they have all been finished. I will show you a couple of pictures. That's really good progress we've made there, and the installation is they're progressing in full swing. And then one of the resulting challenges of that is we have to connect the power converters from these new galleries that we produced, that we built into the existing tunnel. And that means we have to carry currents of 100 kiloamps, about 100 meters from the new galleries to the existing tunnels. A big challenge. If you do this with water-cooled copper cables, you would have to face immense cooling power and electricity bills due to that. And we adopted a new approach here. So we took a high-temperature superconductor, magnesium diboride, as a cooling system, which is capable of carrying over 100 kiloamps over 100 meters without any ohmic losses. It requires a cooling temperature of about 20 to 30 Kelvin, and that temperature you can provide by just boiling off liquid helium that we have in the magnets anyway in the cryostats in the main tunnel, and we just let it boil off and the gas goes through this flexible cryostat up to the new galleries and to the feed boxes and make sure that the superconducting cables are cool enough to be superconducting. And I will give you a couple of more pictures later on. But that was one of the new technologies we had to develop for the high luminosity LHC. As the next challenge, I want to highlight to you is the interaction region and the number of bunches that we have. So I mentioned to you already, we have the focusing elements where the beams go on the same trajectory, and then we have the separation recombination dipole magnets, which separate the beams into two separate apertures over the arc, where they then go in opposite directions along the machine until the next interaction point. So the challenge here is that we have about 130 meters from the first separation recombination dipole magnet on the one side to the other, where the beams share the same vacuum chambers. And even in the D1 magnets, they have some common space that they have to share. So you talk about 150 meters where the beams share the same vacuum chamber. And we plan to have in the LHC about 3,000 or 2,800 bunches with a 25 nanosecond bunch spacing. That means we have every 3.5 meters a potential collision. That means over all of this area, we have many, many potential collisions, but we only want to have the collision in this one point in the center of the detector. So we have to make sure that we avoid all of these other collisions. And the only way to do that is by introducing a crossing angle. So we actually introduce an angle between the two beams so that they only collide at the one location in the center of the detectors, and all the other parasitic potential collision points are separated so they don't see each other. Because we have high intensity bunches, they have nonlinear fields from the electromagnetic fields. In order to minimize this long range beam interactions, the separation has to be sufficiently large. So we have to make sure that the beams are separated by at least 10 sigma for these parasitic encounters. And again, this is one of the reasons why we want to have large magnetic apertures in order to have enough space for these large crossing angles. And yeah, the biggest drawback of this in the end, that I comment in the next transparency, is that the large crossing angle has an impact of the actual performance level of the machine. And that I want to illustrate by introducing to you the geometric luminosity reduction factor. This is a formula. Never mind this. I think illustratively you can think of by two bunches which are longer than they are actually wide and overlapping. And the luminosity is actually given by what we call as a luminous region. That's the region where the two bunches actually overlap. And you see if you have a crossing angle between two long bunches, is that the actual region where the overlap becomes smaller. So the luminous region becomes smaller, and the effective cross-section at which they interact with each other becomes bigger. And both of these are mechanisms that actually reduce the luminosity that you would expect for a head-on collision when the bunches perfectly overlap. And I want to illustrate that to you with giving you some examples for this geometric reduction factor as a function of the optical design function that we designed the machines for. So the LHC commissioning started with an optical beta function value of 80 centimeters. So for LHC commissioning, we lost about 10% of the maximum potential luminosity. It's not too bad yet. The nominal LHC design has an optical beta function of about 0.5 meter, so they would lose about 20% of the maximum potential performance. Still not too bad, that's acceptable. But for high luminosity LHC, we want to operate the machine between 10 and 15 centimeters beta star. And that means without any corrective measures, we would lose about 70% of the actual performance potential of the machine. And that is a really inefficient way to operate the machine. And to overcome this, we introduced transversely reflecting devices, which we call crab cavities. So they deflect the head and the end of the bunch in opposite directions so that the bunch doesn't go ahead straight along as the path of the crossing angle, but gets slightly flipped. So it looks a little bit like a crab walks on the beach, hence the name of crab cavity or crab cavity deflecting devices that we have. And with that, the effect is that at the actual interaction points, they don't have then the overlap angle, but they actually overlap perfectly. So you recuperate ideally the whole geometric reduction factor. So for this, we want to have independent crab cavities or deflecting devices for each interaction point. And since this is a novel design, we have never done this in a proton machine before. We've worried a lot about noise from these devices onto the beam sizes and potential beam losses, and the ability to actually control precisely enough the two devices left and right from each interaction point. So this really was a challenge for the technology development. And it had to fit into very challenging space constraints on top of that. So in the end, we adopted two designs, one that we call the RFD dipole and one that we call the double quarter wave deflecting cavity. So they're more, they look very similar, but they're essentially rotated by 90 degrees. So one is adapted for horizontal crossing angle, the other one for vertical crossing angle, effectively. And so we need 4 cavities, 4 interaction point per side, so 16 in total. So we need 8 per type. And then we have 2 of these cavities always installed in one common cryostat. Since they're superconducting devices, they need to be cooled by helium. So they have to be in a cryo vessel, always 2 in one tank together. And that means we have to have 4 cryo modules per crab cavity type. And in the installation, we have 2 of these cryo modules on each side of the interaction points. So with that, I come to the general summary of the technology challenges that we developed or addressed for the high luminosity LHC. I mentioned to you already the focus in quadrupole magnets. So this is what Lucio Rossi, the previous project leader, always called the crown jewel of the high luminosity LHC project that got to be developed. I mentioned to you the new underground areas, the access shaft caverns and the galleries. I mentioned to you the superconducting link, the crab cavities. On top of that, we had to develop new separation recombination dipole magnets. We had to develop new collimators for more powerful beams in the main machine for proton operations, and for the ion operations, we had to develop crystal collimators, all developed. And for the civil engineering, we finished that in 23. The collimators already installed in the machine, half of it or more than half of it, and already used in the operation nowadays in this run. For the crab cavities, we're in series productions. For the superconducting link, we have the complete prototype validated, and we're now in the series productions of the system. For the triplet magnets, we have almost half of the system ready for installation, so we're making progress there. And for the new separation recombination dipole magnets, also we have the first series magnets already produced and delivered to CERN, and we make very good progress there on each front. Just in one transparency to highlight to you that CERN is not doing this in isolation. So this is not just a CERN project. We do this really in a very broad and strong international collaboration. So we work really with many, many different countries together, American partners, a lot of European partners, Canada, Japan. You see that in the flags. I don't want to go through the whole list. Just want to highlight to you, really, this is a truly international collaboration that we built for the High Luminosity LHC project. So since I'm more than halfway through my presentations, I just want to flash a couple of nice pictures to you to show you really that when I talk about progress of hardware, this is really tangible. You can go into many areas at CERN, go into the various halls, test halls and installations, and you actually see the hardware building up. So this is for our crown jewel, as Lucio would call it, our triplet magnets. These are the type of magnets that we build in-house at CERN, the MQXFB type magnets. You see two prototypes already installed in the IT string, which I will introduce to you in a couple of transparencies. Then we see that 3 of them already fully validated. They're ready, and they could be installed anytime the machine is ready for installations. The magnet 6 is still on the test bench, but has passed more than half of its validation program. It reached the nominal performance already. We do another thermal cycle, and then this magnet will also be fully validated. And with the 6 magnet validated, we have half of what we need for the installations in the Long Shutdown 3 already validated and produced. So it's really a major milestone. And you see that the next magnet, so we need then 4 more from our production, 7, 8, and 9 already in a very advanced phase, and also will come over, by next year, we will have also those ready. Just to not forget our American colleagues, so they built the other half of these focusing triplet magnets, which we call the MQXF-A magnets. So these are the Q1 and Q3 magnets. I don't want to go through the details, but just to flash to you here, that also make really a lot of progress. The coils are almost all produced. They will finish the coil production soon. At Fermilab at Berkeley, they finished the coil production. For the magnets, they assembled already more than half, almost 2/3 of the magnets are assembled. Over half of them are validated in a vertical test, and now the main focus is the assembly of them in the horizontal cryostat. And there we have 3 of them produced. Then the next 3 are in the line and expected by the end of this year. So also there we make good progress, and that is moving forward. Couple of pictures for the civil engineering underground structures. So this is from the ceremony that we had in 23, celebrating the end of the civil engineering. You see Fabiola with delegates inspecting the new cavern. You see here the main big gallery as it was fresh after installation. And you see here a look up in the new access shaft, and then a picture of us all celebrating this moment in time. For each experimental point, so Atlas and CMS, we built 5 new surface buildings. They all have been completed too. So you see here the surface building completed, and they are now being equipped with technical infrastructure. And here's a picture at the end of last year, just to show you that in this new underground galleries, really things are building up. We have now the ventilation ducts already in the access shafts. We have here the smoke extraction system in the main gallery that we built, and the first power converter cases are being installed there. And the next thing we're looking forward to is the installation of the cryogenics distribution line in this new underground gallery. A picture to the superconducting link, the magnesium diboride superconductor. This is a cross sections of what this looks like. So you see here in red is mainly just the copper cable that gives the mechanical structure and the stability. The actual superconductor are the small green dots. And you see here a set assembly of 7 cables with various current gratings, so up to 18 kiloamperes and some of 6 kiloamperes and some of 13 kiloamperes. All of that, the whole cable in total can transport over 100 kiloamperes as it's fully powered. This is a picture of the flexible cryostat in our test facility SM18, where it's prepared for test and validated. So all of this in a flexible cryogenic cryostat. And this is a picture from the celebrations where we celebrated the successful validations of a full prototype over 100 meters long with the feed boxes on both ends. Major milestone. I want to show you a couple of pictures from these deflecting crab cavities, or F deflecting cavities. So this is the double quarter wave design that we've done. This is a prototypes built at CERN for installation in the SPS. So we built the cavities, assembled the cryostat, and then installed this cryostat in the SPS, where we actually tested the deflecting the deflection of these cavities on the proton beam in the SPS. And you see here beautifully, this is when the system is turned off, and this is when it's turned off. This is the longitudinal length of the bunch. So this is the head of the bunch, this is the tail of the bunch, and this is a transverse dimension. So you see nicely how the bunch is deflected. This is from tests that we performed in the SPS from 2018 to 23. So this type, the double quarter wave prototype, has been taken out. This is now the prototype of the other type, the AFD crab cavities, which has been built in collaborations with our UK partners. Here's the cryo module in preparation for installation in the SPS. This has been now installed in the SPS. It's already cooled down, already has seen beam, and we're looking forward in this year for first dedicated test of this new second type of crab cavities with beams in the SPS. So that's another highlight to look forward to. With that, I come to the IT string that I promised you already in the beginning. So what is the IT string? This is the overall picture of the LHC layout. This is here the CERN side, 0.1 Atlas, and here you see the CMS side. And if we zoom into the CMS side, you see on the left side, this area, there we try to replicate all of the magnet arrangement that we have in the tunnel on a test facility on site at CERN, in the test facility SM18, for those of you familiar with the CERN naming. And there, the magnet arrangement just fits perfectly on the back wall of our test facility SM18. So this is what this looks schematically in a drawing. So you have here the magnets going from the Q1 quadrupole up to the D1 dipole magnet, all assigned with the feed boxes. The new galleries that we built in the LHC underground are mimicked by a metallic platform, which hosts all the equipment that in the high luminosity LHC area will be in the underground areas. So the power converters, the quench protection systems, and all of the electronic racks. Then the superconducting link with the feed box goes all along the superconducting link. It feeds into the magnets here. So really to reproduce the full system and to test and validate the integrations, the interconnection challenges for these new magnets, and the powering of these new superconducting magnets. Niobium-3 tin has different properties, and we want to make sure that we understand the system behavior of these magnets before we really go into the machine operations in the LHC. And this test facility is the ideal point to address that. So the installation is in full swing. Almost all magnets are there already. I think the last magnet will be installed next week, and then we start the interconnection of the magnets. We already started the pulling of the superconducting cable that makes the electrical connections of all the elements. And then the second half of this year, the interconnection should be finished, and we plan the cool down of the string test. And then by the end of the year, we should start the first powering of the system. That will be really a major milestone for the project. Just in pictures to show you that we have the elements. So these are the prototypes made at CERN, Q2A and Q2B, that we have already and are already installed. Then we have from our American colleagues already Q3 magnets, the corrector package we have done, and the D1 magnet we have built, and it has been already moved to the IT string. And the Q1 magnet is we have already at CERN from our American colleagues. That's the only one that is not yet in the IT string, but that will be moved over the next days and be installed there too. So in pictures, if you go to SM18 now, this is what you can see there. So you see really beautifully from the Q2 magnets all the way up to the D1 magnet. The only problem is that the IT string is so long that it's very difficult to capture in the picture. We tried in various aspects, but it's so big that it becomes hard to capture. But really, stay tuned for this. And I think with that, I'm at the end in my summary. I just want to highlight to you a book that we published last year. So this came out in 24, not last year, the one before last year, published in 24. It's really the proper descriptions of the full high luminosity LHC project after 2016, after the approval and after the rescoping of the project. So you find a lot of detailed information in there. And this has been published as open access. So you can buy it, but you don't need to buy it. You can just follow the link that is indicated here and you can download it and look at it and get much, much, much more background information to the project if you're interested. And with that, I think Rachel and Irena, I'm done. And I'm open for questions.
Thank you, Oliver, for this overview and fascinating upgrade. Well, I see, yeah, let's jump now into the question and answer session. Let's open the floor to questions from our participants, and I've seen already one in the chat. So Adam, question is, with stronger magnetic fields of dipole magnets, it will be possible to increase the collision's energy as well?
Yes, that would be possible, but for the project, we only increase the quadrupole magnets, so the optical lenses, which allow us to focus the beams to a smaller spot size. We still keep all the dipole magnets of the existing LHC in the arcs, and they define the energy of the beam, and that will be the same. So that we face the same limitations that we have for the nominal LHC. There are plans, though, for future upgrades to replace also the arc dipole magnets by higher field magnets. There are proposals for high energy LHC, but that would be a different project and on a different time scale and has not even been yet fully developed for implementation. So high lumi will have the same energy exactly as LHC.
We have another question from Tamara. How exactly do the crop cavities tilt the bunches? How can these new technologies be reused in the FCC?
So the field has to vary very quickly. So essentially the bunch goes through there as the field just goes through the 0 point of the polarity change of the transversely deflecting field so that the head and the bunch see opposite fields. And it has to be very well synchronized to the passing of the bunch. But it's by applying a time-varying transversal electric field that has a different impact on the head and the tail of the bunch. So the first cavity on the entrance to the detector starts the deflections of the head and the tails. And as the bunches go into the action points, they start tilting. And then in the detector, they overlap tilted. And then at the exit, there's another set of cavities which tilts them back again to the nominal orientation. There are indeed many other applications for other accelerators. So I think if you follow the electron-ion collider project in the US, built at Brookhaven National Laboratory, they picked this idea up and they have this in their baseline too. And they fully rely on our R&D development for these cavities to use them for the electron-ion collider. For the FCC, yes, probably for the hadron machine, it will also be interesting. And applied for the lepton machine, it's not as interesting. It's mainly relevant for very long bunches. And for the lepton machine, the bunches are too short. They have a different optimization scheme, which is called the nanobeam collision scheme, and it doesn't rely on crab cavities.
Yeah, Frederick, please feel free to unmute yourself.
Hi, thank you, Irene. I'm Frederick Micolon. I work for Brookhaven National Lab, actually. And you show in 2024 you had a steep increase in luminosity, and I was curious where does that come from? That about factor 2 that you got in 2024?
Yeah, it was really AA is injector complex upgrade. I didn't mention that at all, and to be fair, I should have. So we had in the first long shutdown 2018 full refurbishment of the whole LHC injector complex, and that provides already the higher beam intensities that we need for the high lumi LHC period. We're just not capable yet of digesting it, but it allowed us to push really the peak luminosity a factor 2 above the nominal design. So that was one push. And the other one is really that the machine worked incredibly reliable and efficiency, and it highlights how important the machine efficiency and reliability is. And so it's one thing to push the peak performance, but you really make the big gains by making sure the machine runs like a clockwork and doesn't have any faults and any failures. And that's what you see in the last year's operation. It was just like a clockwork without any faults and failures, and it was beautiful.
Right.
And so
for the Just as a follow-up, sorry, for the injector upgrade, did you improve mostly the bunch intensity or the emittance?
Both was improved. The bunch intensity mainly by changing our proton linac. We had a proton linac and we changed it to an H- injector, so that's a linac 4. Now we can have high intensities overlapped injected into the PS booster. That's very nice, and we increased the extraction, the injection and extraction energies of the booster and the PS. That allowed us to also reduce emittances, to have small emittance, and then it's a power upgrade in the SPS to cope with these higher bunch intensities.
All right, thank you.
Sure.
We have 2 more questions from Tamara. So related to the other one, she meant which new technologies can generally be reused for the FCC, not only the crop cavities. And you can reply to.
Yeah, but absolutely. I think the high luminosity LHC one should really sell as a technology developer for general accelerator projects, and I think they have applications in many other potential projects. And I think yes, the FCC will certainly be one of the first machines trying to benefit from the developments that we have. Whether that's a focusing quadrupoles, whether that's absorber materials for the beam dumps, that really, it depends on what implementation of the FCC you're talking about. Since High Lumi is a hadron machine, most of what we develop will have an impact for the FCC HH machine, for the lepton machine, maybe to a lesser extent. But yeah, a lot of the technologies can be directly applied. Over.
And she would also like to know, how can the HL-LHC serve as a proof for dark energy?
I didn't quite understand that. Say that again. How?
Like, how can the HL-LHC serve as a proof for dark energy?
For dark energy or dark matter. Yeah, well, of course it can. You can have the hope that we see more there, but I think it's difficult to predict anything, right? So I think, yes, by having more data, you will have more higher precisions in the results. And if you have higher precisions, that might give you an indications where you diverge in your measurements from the predictions of the standard model. And once you see that, you might get indications what the dark matter and dark energy is. But yeah, it's difficult to predict really anything and how we will do this. But obviously, more data will help there, and that's the first step to do. Yeah.
We have another question from Maurice. Will the success or the results of HL-LHC influence the design and or the go-ahead of the FCC?
As we said before, I think, yeah, obviously, I think for FCC-HH, there will be a very clear link of what technologies can be used. FCC-HH thinks, for example, about niobium-3 tin dipole magnets in the whole, in the arcs for the bending of the magnets. This technology really has been developed now by High Luminosity LHC. So niobium-3 tin is an established magnet technology. We showed that we can build magnets out of that, and that, yes, any other project can pick up. And again, the lepton machine FCCE is slightly different. So there, the synergy is maybe less obvious and less extreme, but for the next hadron machine and the FCC hadron implementation, definitely.
So another question from Adam. Will all experiments be able to digest this new high luminosity?
Yeah, so that's an interesting question because we started the high luminosity LHC mainly with assumptions we mainly cater to Atlas and CMS. Then it became, after the initial success of the Alice detector, rather quickly clear that they won't have an upgrade too. They want to also have more ion luminosity. So the ion upgrade became an integral part. And so then the only experiment left, which didn't have a major upgrade, is LHCb. And they implement now a phase 1 upgrade, also one in the Long Shutdown 4. And they're even dreaming about a bigger upgrade. So no, they want to prepare also for more data and to be able to digest it more. So to come back to the questions, I think 3 of the 4 detectors are already fully prepared for the higher data rate of the high luminosity LHC. One should also not forget that for ion operations, we are already in the high luminosity LHC mode because Alice has finished its upgrade already. And with the upgrade of the injector complex, we really boosted the ion operation performance. So they're already fully high lumi levels. And for the protons, yeah, Atlas and CMS are in the upgrade phases, and LHCb is also thinking strongly about upgrading, but will come slightly later.
Right. Another question from Emmett. Are any of these technologies applicable to a potential future muon collider?
Absolutely. So I think high lumi is a magnet technology developer, and one of the key ingredients you need for a muon collider are very high large aperture magnets for the fast ionization cooling and for the fast acceleration. And there again, OBM3 tin development that we've done is vital and is a key ingredient.
And Tamara would like to know, oh, sorry.
And maybe just to add to that too, I think also in terms of absorber materials, machine protections, that for muon collider, you will have very intense proton beams first going on a target. And for that, you need to have all of this collimation target absorbers. And there, all the development of the high luminosity LHC, I think, has a direct application into that design.
I will allow myself to ask you,
Sure.
You mentioned the high luminosity involves deep collaboration across many countries. How was that international cooperation shape the project's progress?
Well, I think the international collaboration shaped the project quite a bit. I mean, from the beginning in the European funded design study, we set it up as an international collaboration. And CERN did never do this alone in a standalone phase. So even there, we had a broad international collaboration, and that was leveraged in the end for the final approval in terms of in-kind contributions from the various countries. So about 10% roughly of the whole high luminosity LHC budget comes from in-kind. And I think there's an intimate relationship between it being an international project, and so we are forming our international collaborations, and the collaboration formed the project to a large extent. So I think it's a two-way road, I would say.
Thank you, Oliver. So yeah, I'm not sure if it's time to close the session. Frederick, thank you. Feel free to ask.
Yeah, maybe one last question since we have time, and I hope it's not a bit of a provocative question, but we know the development of the niobium-3 tin magnet was a bit of a painful development. What's your opinion? Are we out of the woods? Is it a mature technology now?
You have multiple layers of questions, right? I mean, I think any new technology development, you can call it painful, but it's also very exciting, right? Because you discover many new effects and many new phenomena that you didn't have on your radar before. So I think that's by definition, if you do something really new, you're prone to see surprises. So I think that we've done. Are we out of the woods? I think for the high luminosity LHC quadruplets, yes. I mean, I'm 100% confident these magnets will work. We will be ready in time for installation. There's no issue with that. Are we out of the woods for a next future project, in the sense that would I be confident that we can give now an OBM3 tin magnet design to an industry and ask them just to produce 1,000 or 2,000 of them? I would be careful. I think there's still a lot of work to be done, and not impossible, but I think that's right now we talk about bespoke magnets, right? All of them are really done in bespoke efforts by really a customized approach, one by one, with very, very careful quality assurance. If you go into a larger scale, industrial scale production, it's a different optimization that you have to go through. I showed before the picture of the Tevatron Hera to RIG and then LHC. I think the painful part was with the Tevatron, right? When they made the first magnets, they had persistent currents. It was an absolute, not disaster, but it was a real surprise how to cope with these time dynamic effects, and they struggled with that. Hera addressed this aspect just to cope with the time varying effects, so that got solved. And then RIG was the only one, the first machine which really went to an industrial optimization process and say, okay, we now understand the technology. Now we want to optimize it so our industry can produce it. And I think here we're still in the phase with an OBM3 tin magnets where we saw a lot of technical problems during this R&D phase and this first production. I think they can be now translated into the next steps, but I think you still have the industrialization in front of you, if you ask me.
And I will just add that, yes, we're happy with our magnet, the RIG magnet, still perform after 25 years. And we have other issues, but the magnets are fine. So yeah, but anyway, thank you for your answer.
Thank you, Oliver, again for the presentation and for answering those questions. And thank you to everyone in the audience for your engagement. I hope you really enjoyed the session, and I would now like to turn the floor over to Rachel, who will officially close the event.
Thank you so much. So many thanks to you, Oliver, to Irene, and also my team, Elena and Simona, who helped organize this event. So it's been absolutely fascinating, this presentation, and I've learned a lot. And I thought maybe we could invite you back in a year and a half or so, whenever, so you can give us an update on how everything's going.
It was a pleasure. No, super.
Thank you so much. Really, very many thanks. I think there's also a lot of interest about what comes after HL-LHC. So some of you might have seen that CERN released the report on the feasibility of a possible future circular collider on the 31st of March, and you can actually download it from home.cern. And then there will be a symposium, an open symposium, in fact, taking place in Venice in June. It's a community-wide event to gather or debate the future orientation. So we know that people are also very interested, well, our alumni are very interested in this topic. So we are planning a couple of news from the lab, one which will be following the FCC week, and then another one following the symposium in Venice, which will probably happen, our event will probably happen in September. So that can, we've had like a close future view, thanks to Oliver with HL-LHC, and then, you know, we'll see, we don't know, we'll see what, with the news from the labs covering those two topics. So I hope everybody will also be able to take part in those.